So students, today we discuss the chapter work, energy and power. All the three terms work, energy and power we have already studied in junior classes, but here we discuss in brief. In day-to-day life we use the word work done very commonly. We have to do a lot of work from morning to evening, morning to night, but in scientific it is not considered like a work done. In physics, work done is to be count when some force is to be applied on object and it must be displaced. Then it is counted in terms of force, work done. So work done is to be defined by a symbol W, and it is the product of force and displacement. If we expand it, because of dot product, that is scalar one, so F S and along with angle cos of theta. That means in mathematically when we calculate the work done, so angle plays an important role. How much angle between force and displacement are. Okay. On behalf of this angle, we have to categorize the work done in three parts. So before we go to types of work done, first we come to the unit part. If we discuss the unit, so force is in Newton, displacement is in meter, and angle it have no dimension. So Newton into meter. This is the unit in order to calculate the work done, and the product Newton into meter is said to be joules in MKS system. Similarly, if we go to CGS system, that is centimeter, gram and second. So this Newton is to be converted into dyne. This meter is to be converted into centimeter, and again the product of dyne into centimeter, this is known as erg. So either we have to use the unit joules in MKS system or erg is in CGS system. And like there is a relation between newtons and dyne in force, similarly one relation is between joule and erg. 1 joule work done is equals to 10 raised to power 7 ergs. So this is very important relation between joule and erg. Like in force, 1 newton is equals to 10 raised to power 5 dyne. So whenever we solve the numericals, we use these two identity in our mind. 1 joule is equals to 10 raised to power 7 erg and 1 newton is equals to 10 raised to power 5 dyne. So this is the concept regarding work done. Next we come to types of work done. Next we come to types of work done. So if you go to types of work done, so work done is to be categorized in three parts. Number one, this is positive work done. Second one is negative work done. And third one is zero work done. So work done is to be categorized in three broad parts: positive, negative and zero. Now we see which type of work is to be said to be positive, negative or zero. So we have some conditions. If we talk about the positive work done, so in positive work done, when force F and displacement are in same direction, so when force and displacement are in same direction, then it is said to be positive. For example, if we take one example, if we apply force of an object of mass m, suppose, along the x direction. So when we apply the force F on block M along the x direction, so obviously whenever the direction of force, object must be displaced in same direction. So on account of this force, this box is to be displaced. Suppose it travels s distance and this is the second one position. So here force and displacement are in same direction. So if we talk about the angle, so here angle theta is to be 0 degree because force and displacement are in same direction. So what we have to conclude, theta is equals to 0. So if we go to formula F dot S cos, and we have to replace theta by 0. So cos 0 is equals to 1. So work done is equals to F dot S only. If we go to negative work done, so when force and displacement are opposite to each, that means the direction of force and displacement is to be just opposite. So in this situation, when force and displacement are to be opposite, so obviously when force and displacement is to be opposite, so angle must be 180 degree. And we see where is the situation where we get force and displacement are opposite to each other. So there are so many examples in day-to-day life. Whenever we apply the brake in moving vehicle, so it suddenly stop. Okay. So on applying of brake, it suddenly stop. That means now displacement is just opposite because of frictional force. Similarly, if we take two bar magnets, north and south pole, and another one is again south and north pole. If one of the magnet move towards the another magnet having south pole, so between south and south again repulsion take place. So this repulsion shows force and displacement both are opposite. If we come to formula, so F dot S and cos of 180 degree. So as we know, cos 180 is equals to minus 1. So in this situation, what we get, minus F dot S. Because of this negative sign, this work done is said to be negative. Okay, so this is the second one, identity, which we are used to solve the numericals. Last we come to zero work done. In zero work done, when force F and displacement are perpendicular to each other, okay, then this is the situation for zero work done. So here force and displacement are perpendicular. Now we see where is the situation where we get force and displacement are opposite. So in order to understand this one, suppose we take a luggage on our head and then we have to move. So in this situation our displacement is along the x direction and load, this is weight. Either we can say force or W because both is equals to mass into gravity. So whenever we take the load on our head and we go straight line, so it makes always 90 degree. So in this situation, work done is to be 0. That means W F dot S, and again we come to angle, so cos of 90 degree. So cos 90 is equals to 0. So in this situation, work done is to be 0. Okay. So this is the condition where we get the work done is to be 0. Next we come to how to calculate the work done when force or displacement is to be variable. So next we calculate work done by variable force. So when force is to be vary from initial to final, then how to calculate the work done? So this is the situation where we see object is moved from initial to final state F. In this situation, displacement is to be vary from initial to final. That means every time we see, if we draw the perpendicular, there is a variation in displacement. And similarly, if we draw the perpendicular towards y-axis, so again we see there is a variation. So in this situation, how to calculate the work done? So here we use the integration technique to find out the work done. So here we find out the work done in two methods. First one is geometric method, and second one is integration. So either we have to choose geometric or integration method. But if we take the geometrical, so this process is to be very large, because now we see there is a first rectangle, then second strip, then third strip, then fourth strip, then fifth and sixth and so on. So every time we have to find out the area of each strip and then we add. So this process is to be lengthy. So in order to avoid this, we use the integration technique. So in integration technique, we take first any small strip. Okay. For example, if we define A, B, C and D. So we calculate first for only A, B, C, D and then apply the limit to find out initial to final. So in this situation, work done is to be written as dW. This means small work done. This equals to force into displacement ds. Okay. And for integration, this del symbol is to be converted to d, w, f remains same, displacement, this becomes ds. Equation number 2. Okay. Now we see displacement. So displacement is vary from initial to final. That means it has some well defined limit. Okay. So now we apply the integration both sides having limits. Displacement limit is x initial to x final. Now integration of dw becomes only w. Force is outside. Integration of ds within limit initial to final. Equation number 3. Now w remains same. F is outside the integration. ds. So integration of ds becomes only s and its limit is initial to final. Now upper limit minus lower limit as per the property of integration. So w is equals to f x final minus x initial. That means by knowing only initial and final displacement, we find out how much work is to be done to move the object from initial to final. So this property is to be utilized again in numerical, where displacement varies from one place to another one on applying a constant force, because here force is to be constant. Okay. Next we go to second part of the chapter, energy. So next we come to energy part. Energy. This term is correlated with work done. That means capacity or ability of doing work this is said to be energy. How much capacity or ability of doing work by either machinery or by us. So this is counted energy. Now there are a lot of energies, as we know: nuclear energy, thermal energy, chemical energy, kinetic energy, potential energy, okay, tidal energy. But in this chapter we focus on only kinetic energy, second one is to be potential energy, and third one is mechanical. So we mainly focus on kinetic, potential and mechanical. Kinetic energy. So this is the energy possessed by an object due to change of its speed, or we can say change of its motion, and this is to be defined by kinetic energy. This equals to half m and v square. So what we see in this identity, half remains numerical value, velocity is to be changed but mass never change. That means kinetic energy because of only motion, or we can say change in velocity. Next one is potential energy. This is to be defined by PE symbol, and this is the energy due to change of position, or we can say change in configuration. For example, second hand in a clock. So when it is second hand is to be rotate, so their position or configuration is to be continuous change. Similarly, if we drop the chalk from one place to another place, so again what we have to see, if there is a change in their position. So this is counting potential energy, and its identity is mg and h. Again, mass remains constant, gravitation acceleration, it is to be constant, and its numerical value is 9.8 meter per second square. So only one parameter is to be here variable, height. This shows only position or configuration. And last we come to mechanical energy. So in mechanical energy, this is the sum of kinetic energy as well as potential energy. So it is to be represented by Ke plus Pe. That is sum of kinetic and potential. If we talk about the unit, so either kinetic, potential or mechanical, each have same unit like work done. So in MK system, either we have to calculate kinetic energy, potential or mechanical. So every time we use the same unit, joule. In MK system and for CG system, it is to be erg. Okay. And as we know from energy conservation, energy is neither be created nor be destroyed. It converts from one form to another one. If we look the cell, in case of cell, what we have to see here, during the making of cell, we use some electrolyte, and this electrolyte is to be converted into light energy. So here chemical energy is to be changed into electrical. So this also shows energy remains conserved. Neither we create nor we destroy. It converts from one form to another one, chemical to electrical and so on. Okay. Thank you. Next we see kinetic energy is to be defined by half mv square, potential energy is to be mgh, and mechanical, it is sum of kinetic and potential. So how this equation comes? So one by one we see. First we see kinetic energy. So as we know from identity, it is to be represented by half m and v square. So how this comes? So in order to prove this equation, let us consider an object of mass m which are placed on the surface x and y. Okay. When we apply some external force towards y, so obviously this object is to be displaced in same direction. Now let's suppose it is to be displaced by an amount s. So we see some work is to be done because this object is to be moved from one place to another one. So here some work is to be done, and this work done is equal to force into displacement. Say equation number 1. And this work done is to be counted in terms of energy, because as we know the capacity of doing work is said to be energy. Okay. Now we see force, this equals to mass into acceleration, and displacement is already there as, say, equation number 2. Now again mass and displacement we have already well defined. Now acceleration. So how to calculate this acceleration? So we use here Newton's third equation. By third equation, v square is equals to u square plus 2as. So from starting, object is to be stationary. That means its initial speed is to be 0. Okay. So in this equation, we replace u is to be 0 because object is stationary. Now 2 remains same, a remains same, s remains same. This equals to v square. If we find out from here this equation, a into s. So this as is equals to v square divided by 2. Okay. So equation number 3rd. Now this equation 3rd is to be substituted second for as. So what we have to see, this work done w is equals to m remains same. This a into s is to be replaced by v square by 2. So this equation is just similar to formula of kinetic energy, half mv square, and we can say this work done is to be equal to kinetic energy, and this equals to mv square by 2. So this is the proof of kinetic energy. Okay. Next we come to potential energy. So next we come to potential energy part. So as we already identified, potential energy means the energy possessed by an object due to change of its position or configuration. Okay. So now we look one example where position is to be changed. Suppose an object of mass m are placed h height above the building. Okay. And this object is to be falls downward on surface xy. Okay. So in this situation we again find out work done, and this work done is to be counting potential energy. So work done means force into displacement. Okay. Now again work force is equals to mass into acceleration along with displacement s. Say equation number 1. Now what is the change here? Here object m is to be freely fall under gravity. That means normal acceleration a is to be replaced by g. So this is the first change, m, a remains g, and second one, distance. So here s is to be replaced by h, because here s distance is to be replaced by h height. So this s is to be replaced by h. Now this work done is equal to potential energy. So this is the proof of potential energy. Even an object change of its position or configuration, this is said to be potential energy. Last we come to power. What is power? So in power, now rate of doing work done, that means W divided by T, कि how much work is to be done in a given time interval. This is said to be power. If we come to unit part, so work done joule and time is in second. So joule per second is the unit of power, and the combination joule per second is also known as watt. So what is the unit of power? In day-to-day life we use electricity appliances, tube light, bulb. So every electrical appliance is having some power, and this power in terms of watt. How much energy is to be consumed by tube light, bulb, geyser in per second. So this is to be counted in terms of watt. So this is the normal unit of power. Similarly, one more unit is to be there, that is known as kilowatt hour. This is said to be commercial unit, and this equals to 3.6 into 10 raised to the power 6, and this also known as unit. As we see, your household electricity bill comes in units. How much unit we have to consume in a month? Okay, so this is to be calculated in terms of kilowatt and hour. This is 3.6 into 10 raised to the power 6 unit. Okay, one more unit is to be there for machinery. This is called horsepower. So 1 horsepower, this equals to 746 watt. This unit is for machinery purpose, and generally we have to use this unit for electricity pumps. Okay, and in power plants also. So we have 3 units: power, watt for electricity, similarly kilowatt hour, this is said to be unit also for commercial unit, and third one for electricity appliances like motor, refrigerator, this is horsepower. So this is the one of the biggest unit in power. Thank you.